Let me start with the motivation of this work. There are many 3D modeling software that enables the users to create almost any kind of 3D objects. However, creating a 3D model is still a tedious task, especially for novice users. It takes a lot of time to learn how to use the modeling software, and manipulating each point and edge is very time-consuming, even for expert users. Procedural modeling is a generative content creation technique using grammar or program. Once a grammar is defined, a wide variety of 3D models with rich details can be created. For 3D building, Wanka et al. 2003 used split grammar, and Mueller et al. 2006 extended for more complex shape of buildings using a shape grammar. However, creating a grammar requires programming skills, and it's hard to control the output. Another approach for content creation is sketching. Sketching is a natural interface for humans. Everyone can draw objects without any special training. This idea motivates many sketch-based modeling methods, including TEDI, polyhedral scaffolds, and cross-section lines. However, the output 3D model is too faithful to the user's sketch, so user has to draw object very precisely and in detail. To tackle this problem, our approach is to combine the sketch-based modeling and procedural modeling. Our goal is that the user can design an object very intuitively by sketching, while the details are completed by procedural modeling. In this idea, procedural modeling acts as a regularization of sketch interpretation as well as a generator of details. Our core problem is similar to the inverse procedural modeling, which is a problem to generate a grammar and parameter values for given input. So far, the most promising approaches are Markov chain Monte Carlo and sequential Monte Carlo, but these generative approaches are too slow for the interactive application. Instead, we use the convolutional neural network, CNN, or ConvNet to quickly solve this inverse problem. Our approach consists of two stages, offline training and online sketching. We define a set of grammar snippets for each object type, building mass, roof, window, and ledge. And a large number of training images are synthesized from the grammar snippets. Then we train the two types of CNNs, recognition CNN and parameter estimation CNN. During the online sketching, the user draws a part of a building, and the trained CNNs are used to find the best grammar snippet and estimate its parameter values. Then the system generates a grammar and 3D model appears. Please note that the output from our approach is a grammar that generates a 3D model looks similar to the user sketch. First, I will explain our grammar snippets. Grammar snippet is a little grammar that represents a part of a building. We carefully look at real buildings and define a set of grammar snippets. Each snippet is labeled with object type, and its axiom is named start. Also, it may contain one or more non-terminals. Here's an example of our grammar snippet fragment for a cuboid shape of a building mass with one corner cut. There are some parameters to specify the shape, including the building height and two non-terminals, top face and facade. This example defines a mansard roof shape with two parameters, slope and roof height. Note that each grammar snippet has axiom named start. Axiom is a starting geometry, in this case, which is a rectangular shape, but can be any kind of planar shape. And depending on the starting geometry or axiom, the same grammar snippet can generate a different 3D geometry. Using the grammar snippets, a large number of training images are synthesized. We implemented our custom sketch rendering that imitates human drawn strokes. For each grammar snippet, parameter values are randomly selected within a predefined range, and training images are generated using custom sketch rendering. We fix the camera position and viewing direction to reduce the complexity of snippet recognition and parameter estimation. Using these training images, two types of CNNs are trained. Our approach counts on the two types of CNN, recognition CNN and parameter estimation CNN. The first type, the recognition CNN, is to find the best grammar snippet for the user sketch. We use the AlexNet architecture that has 5 convolutional layers followed by 3 fully connected layers. The output from this type of CNN is a probability distribution over the snippets. Instead of training the CNN from scratch, we found that fine-tuning the CNN starting from the pre-trained weights significantly improved the convergence. After the 5,000 iterations of training, training from scratch achieves 78% of accuracy, while fine-tuning achieves almost 100% of accuracy. Here is the example of input sketch and output from this type of CNN. Given the user sketch on the left, the recognition CNN produces the probability distribution on the right. This example shows that the second snippet has the highest probability and is selected. We use 1 recognition CNN per object type. Therefore, 4 recognition CNNs are used in total for our implementation. Once the snippet is selected, the other type of CNN, parameter estimation CNN, is used to estimate its parameter values. We found our custom network, 3 convolutional layers, and 2 fully connected layers works well. The output from this type of CNN are a set of normalized parameter values. Since there is no pre-trained weights available for this type of CNN, we had to train the CNN from scratch, which required more iterations to converge. It takes 3 hours for 80,000 iterations of training using 40,000 images. Here is the example of input sketch and output from this type of CNN. Given the user sketch on the left, the parameter estimation produces the normalized parameter values on the right. We use 1 parameter estimation CNN per grammar snippet because each grammar snippet has different number of parameters. We use 26 parameter estimation CNNs in total. Once the offline training is done, the trained CNNs are used to find the best grammar snippet and estimate its parameter values during the online sketching. For each object type, the user selects an anchor region for the next sketch. At the beginning, the ground plane is selected as a default. The user draws a mass shape for a building, and the snippet and its parameter values are detected by the CNN. For the roof shape, the user selects anchor region by menu or lasso gesture, and the system changes the viewing direction automatically such that the user sketch is best aligned to the training images. User draws a roof shape, and the snippet and its parameter values are detected by the CNNs. Optionally, our CNN can use a few iterations of MSMC engine to refine the parameter estimation. We use distance transform to define a score function. While the CNN already achieves a good parameter estimation, the MSMC refinement further improves the results, especially for complex shapes such as L shape or an U shape. Here, root mean square is relative to the normalized parameter values, and our current implementation uses just 10 iterations of MSMC. Once the snippet is selected, it is merged to the already generated grammar. Since the user selects the anchor region for the next sketch, the corresponding non-terminal is identified, which is top face in this example. And the name of the axon of the selected snippet is changed to the selected non-terminal. As a result, the selected snippet is applied to the anchor region. Here is the resulting derivation tree for this example. The box shapes represent a grammar snippets, while the oval shapes represent non-terminals. When the user selects the anchor region, the corresponding non-terminal top face is identified, and the selected snippet is connected to this non-terminal. This general approach enables applying any kind of grammar snippet to any anchor region. When the user changes the building mass shape, it propagates to all the child nodes in the derivation tree. This is one of the advantages of using grammar. For facade design, we provide more efficient mechanism to subdivide the facade into horizontal or vertical repetition. The user draws lines to specify the floor boundaries, and corresponding grammar snippet is automatically generated. These examples subdivide the facade into floors, and we provide a similar user interface to subdivide the facade floor into walls and windows. This user interface makes the facade design simpler and easier for the users. And during the sketching, the user can see the final expected model at any moment. Predefined default grammar snippet and parameter values are applied to the object types that the user has not yet selected. Also, the user can directly change the parameter values. For instance, the user can change the roof slope, or the user can change the panel height of a dome. Also, interactive grammar editing such as select, move, resize, delete, copy and paste, as well as undo functions are supported. Results. We have implemented interactive sketching application that implements our proposed approach. The user can intuitively design a 3D building grammar by sketching, while the details are completed by our grammar snippets. Our CNN-based approach can quickly find the best grammar snippet and find parameter values very precisely. Changing a cylinder to a cube-body shape propagates to the facade and roof automatically. Here are some of the examples of the generated buildings by using our sketching tool. While the currently implemented grammar snippets are limited, a wide variety of 3D building grammars can be created. The creation time was around 5 minutes for each building. Regarding the offline training, each recognition CNN takes 1.5 hours, and each parameter estimation CNN takes 3 hours to train. It takes around 3.5 days in total to train all the CNNs using GPU. To show the expressivity of our approach, we selected the first 20 building photos from ImageNet and used our sketching tool to create corresponding grammars. While there are some noticeable differences, the generated buildings mostly look similar to the source images. We also selected the first 20 building photos from Flickr and used our sketching tool to generate the corresponding grammars in a similar manner. While currently only 26 grammar snippets are implemented, these results indicate that our approach can create a wide variety of 3D building grammars. Since the output of our approach is a grammar, it is very straightforward to generate a wide variety of 3D geometry by changing grammar snippets and parameter values. For evaluations, we first compare our approach to MCMC. The user draws blue lines, and 3D model appears within 0.3 seconds. Our CNN-based approach can quickly find the grammar snippet and estimate its parameter values very precisely. On the other hand, MCMC requires 10 times more time, and root mean squared error is 10 times larger, or MCMC requires a lot more time to achieve a high accuracy comparable to our approach. Our method robustly can recognize the grammar snippet and estimate its parameter values despite the inaccurate sketches and different sketching styles. If the user draws a shape that is not covered by our snippets, the system finds the closest one. And note that it would be very easy to extend our approach by simply adding more snippets. We also conducted a user study asking each participant to create a 3D building grammar using our sketching tool after a short tutorial. The average number of clicks was around 40, and average creation time was less than 7 minutes. All participants could successfully create a 3D building grammar and corresponding 3D model that looks similar to the target buildings. Conclusions. We propose a combination of sketch-based modeling and procedural modeling for creating a 3D building grammar. Our sketching interface provides an intuitive way for the user to create a 3D building grammar, while the grammar snippets helps completing the details. Also, our approach does not require any programming skills. We define a set of grammar snippets and combine them to generate output grammar. This approach significantly increased the expressivity of approach. We use two types of CNN to estimate grammar snippet and estimate parameter values. Our CNN-based approach can quickly solve the inverse procedure modeling and enables this interactive sketching application, which was not possible by the generative approach. There are several limitations with our approach. Our approach currently does not support rotation, and it is difficult to specify depth for the windows by using our sketching interface, and irregular facade layout is not supported. There are several interesting directions for future work. In our current implementation, the grammar snippets are manually defined, and it would be very interesting to automatically decompose the existing grammars into grammar snippets. Also, while we fix the viewpoint to reduce the complexity of snippet recognition and parameter estimation, the CNN has a potential to deal with arbitrary viewpoint. So we would like to explore this possibility. And last but not least, each CNN takes up over 100 megabyte GPU memory. So our current approach using one parameter estimation CNN per snippet cannot scale to a large number of snippets. It would be very helpful if one parameter estimation CNN could be shared for all the snippets. Finally, we would like to thank anonymous reviewers for their constructive suggestions, Jennifer Neville and Hogan Park, the user study participants, and the following grants. Thank you very much for your attention.